221, I'm getting some very good questions in email and the discussion forum about the concepts behind the Bradford assay. So this is the Bradford assay. So I wanted to make this video to help you to see what is going on here. Now, you notice that the pH is about 0.7 here. So the red form of Coomassie Blue exists when the pH is less than 0.4. This has a charge. The green form exists when the pH is about 1.3. This does not have a charge. Now, the form that we are interested in is the green form because we want to make this complex. You see this protein dye complex absorbs at about 615. That is pretty close to the wavelength that we use to measure the concentration of the protein. So we're looking for this color. We're looking for this complex. We do not measure the absorbance at 650 nanometers. So if this complex forms, we will never see it. We are not looking for the absorbance at 470 nanometers because 470 nanometers is the color or the wavelength of the dye even without the protein. So we're definitely not looking for that, right? So this is what we are looking for. Now, I wanted you to understand that the way that this happens has been poorly understood for decades. And it's only since 2008 that we have in the scientific literature some careful experiments that show what is going on. So at pH 0.7, somewhere between this pH and this pH, we have some molecules like this and some molecules like this at pH 0.7. So when you take the Bradford reagent out of the cupboard or out of the refrigerator at ELAC, you will notice that it seems a bit red or brown because it's the color is somewhere between red and green. All right. So why do we have a pH at 0.7? We have a pH at 0.7 because we want the following to happen. We want this guy to form a complex, meaning to have intermolecular attractions with the protein in this area and in this area. So this is not a charge-charge interaction. This is just polarity, possibly hydrogen bonding there, right? And I think you can recognize what's happening here yourself. Actually, it says right there what's happening there. So we want this to happen, and when this happens, you see, this molecule is no longer part of this equilibrium. So this is an equilibrium. You see, it goes forwards and backwards, just like you had some chemical reactions in Chem 65 or Chem 101 doing. They go forwards and backwards. Now, when this complex forms, you see this molecule, it used to be this molecule, it is not that molecule anymore. It is now in a complex. I know that there's no chemical bonds, but the binding is still pretty tight because there's this intermolecular force and there's this intermolecular force, and I think, yes, there's this intermolecular force also. This intermolecular force right here, this is actually a charge coupling here. So this is a positive and negative charge attraction here. So this is a full positive negative charge attraction, very similar to a salt bridge, which you will learn about in the lecture. Now, so the binding is tight. It is not the case that this is going to very easily come off. All right. So what that means is, when this complex forms, that means one of these molecules has disappeared. It has formed a complex instead. It is, for all practical purposes, a new chemical. Now, it's technically not a new chemical because no chemical bonds have formed, but for all practical purposes, they're stuck like that. All right. So that means one of these is gone. And every time the concentration of this decreases, because of Le Chatelier's principle, which you learned in Chem 65 and Chem 101, the equilibrium here is going to shift to the right. So more green will form, and more red will be consumed as the reaction goes this way. So the more protein you have, the more green is going to form, and the more complexes you're going to get. The more protein you have, the less of this you're going to get. All right? So this is one reason why in the pre-lab quiz you found that the Bradford assay requires a 5-minute wait time. So you mix the Bradford reagent with your protein solution and you wait 5 minutes. Why would you do that? Why would you wait 5 minutes? I mean, most chemical reactions are pretty fast, especially at room temperature, am I right? I mean, maybe, but you have to wait 5 minutes because it may take some time for this molecule to find its way, just by diffusion and by the hydrophobic effect, mostly, into pockets that look like this in the protein, right? And it takes some time for Le Chatelier's principle to take effect here, where the concentration of these guys decrease because they're complexing with somebody else, the protein, and then the concentration of these guys are going to have to decrease to make this one increase again. And so a consumption, eating has to happen. Nature will eat this and spit this out, so we'll have more of this, and it takes time. That's part of the 5 minutes. So that's what's going on with the Bradford assay. I hope that helps. Thank you. Bye.